Chemistry in the AM. I'm Joel Shaduck. And I'm not going to have the screen closed. Okay. We're starting the redox unit, and we've got some handwritten notes to take down. So if you're on video, pause the screen, take these things down. I'll talk about them after people have written some stuff down. So, introduction to redox. Reactions in chemistry can be broken down into two basic types. Metathesis reactions, they don't involve electron transfer. We're actually not doing anything to do with them in this class, but that's the other type. Redox reactions is what we're looking at. And, well, this we're going to learn a lot about. It involves reactions where electrons are transferred from one thing to another. And redox stands for oxidation reduction. It's a combo word. And I'll let you jot these things down. I'll pause the video, write these things down. So as you're going through this, jotting this down, have or are just complete. Redox, I use the term redox all the time, and it's short for reduction and oxidation. People have mentioned they've heard this in bio. And in bio, depends, it says the same thing. It's a memory aid. Leo, the line goes ger. Leo, ger. Leo, L-E-O. Losing electrons, oxidation. Ger, G-E-R. Gaining electrons, reduction. I use oil rig. Same thing. Oxidation is defined as a loss of electrons by a chemical species. Oxidation is loss of electrons. Oil. Rig. Reduction. Gain of electrons. Reduction is gain electrons. We're always talking about oil rig. I think oil rig is shorter than Leo the line goes ger. It's two words. But whatever, I don't really care. It's the same. Leo says ger. There's a lot of different lines with different names. So, whatever. Oxidation can't occur without reduction. They're like a coin. You can't have heads without tails. In other words, a substance won't lose electrons unless something else gains electrons. Right? You guys talked about this with like electron transport chain in biology and stuff like that, right? Right? Is that where it came up? You guys remember? ETC? And you didn't get into the mechanics of it the way we will. Okay. Now there's some terms here, and they're kind of backwards. You'll see what I mean. You're going to jot them down here. The oxidizing agent and the reducing agent. The oxidizing agent causes oxidation, but it actually undergoes reduction. That's what I mean by reducing agent causes reduction. So it's the one that undergoes oxidation. I'm going to pause the video, let people write these things down. Something called half reactions and net ionic equations. Writing oxidation half reactions. Now here's an overall total reaction here. Magnesium plus oxygen. I typed my arrow in there. Gives me 2 magnesium oxides. I'm going to demonstrate this. It won't show up on the video, of course, but I'll give you a chance to write it down before I do. And then we're going to sort this into half reactions. So, magnesium plus oxygen, it burns, we just saw it, and gives off an incredible amount of energy. Lights, very bright. Well, light is an energy. Okay. Now with this, though, we got to sort this out. What happens here? Well, I'm going to make this into an ionic. I can show you the ions on it, okay? So what I'm thinking when I see this is that the magnesium and oxygen inside is Mg2 plus and O with a 2 minus, right? That's a distance. Now, there's a reason why I wrote that out. The magnesium reacts and it forms a compound involving magnesium 2+. I'm not worried about the balance right now. I'm just talking about one magnesium. You guys remember grade 9, and maybe not because COVID and abbreviating classes, grades and stuff like that. Or were you guys sent home in grade 9? Yeah, you guys might not have had anything. I know my students didn't want to do physics. Anyway, adding up the numbers of protons, electrons, and stuff in an atom. Did you guys ever do that? Maybe, maybe not. I'm going to do it as if you didn't. I don't normally do this. But magnesium, this number 12 on the periodic table means the number of protons. I'm going to erase this. You don't have to write this down. I'm going to just say magnesium has positive 12. If it has no charge, that means it has exactly the same amount of electrons. Right? I'm going to erase this. You know? 12 electrons, right? Now the protons can never change. So if you change the number of protons, you've changed the atom. That's physics, so that's a nuclear reaction because it involves nuclear. But magnesium 2+, it still has 12 protons. But the only way to get a 2+ charge is to have less electrons. Does that make sense? Because 12 positives and 10 negatives make 2 positives. Now, have you guys ever talked about ions in that way in grade 9 or 10? Not so much in grade 10. So if you got sent home in second semester, you're taking science 9, you might not. I'm getting rid of that, but this is where this is coming from. So think of this. If you have an element, like magnesium in this case, that means you have equal numbers of positive and negative charges. Electrons equal to protons. The only way to get a positive charge is to lose negatives, right? To lose electrons. That makes sense. You have lost electrons. So what I'm going to put on this blue line as an explanation is to go from 0 charge, magnesium on the left element, each magnesium loses 2 electrons. You're going to write this down. And I use E- as my abbreviation for electron. Should make sense. E for electron, negative for the charge. And then I think about this oil rig. Well, the oil is what I'm going to put this here. Oxidation is losing electrons. So if they're losing 2 electrons, this is oxidation. Okay, let's jot this down. We'll talk about this. Now, switching colors because I'm talking about the oxygen. Now, not to be messy though, I'm going to just sort of start my line and then do it underneath here. Right? You guys see what I'm talking about there. The green line, you don't want to draw it through the blue. So, take a look at oxygen. As an element, one oxygen atom has just as many electrons as protons. So it's like it's got a 0 charge as O2. Now, in order to make a 2- charge, that means it has 2 more electrons than protons. I don't care that it's 16 protons. It's just that it's got 2 more. So to get a 2 negative charge, each, and I'm going to put O as a handwritten O, only so you can tell the difference between 0 and O. Each O atom gains 2 electrons. that's the rig part of this. Coil rig, a memory rig. Reduction is gaining electrons. You're gaining negative charges. So, I'm going to say the compound oxygen, the molecule, is reduced. About that. Now we're going to revisit the first page on my slide of notes. You might have them all on this page. I'm going to read these last things. Oxidizing agent, reducing agent. The oxidizing agent causes oxidation. The actual chemical is reduced. And reducing agent, vice versa. Let's just take a look at this. Magnesium is what's oxidized. Okay? What was added to magnesium? Oxygen, O2. Oxygen caused it to be oxidized. So we would say that oxygen, O2, is an oxidizing agent. And that's historically why it happens that way, because oxygen works. Other things other than oxygen can be oxidized. Anyway, so here I'm going to add in a little bullet here, just so we can get our vocabulary. Oxygen. When I say oxygen, I'm talking O2. I will try to be careful and say oxygen atoms if I'm talking about signals. Oxygen. O2 is the oxidizing agent. Says it causes magnesium to oxide. You might hear the word oxidize. You hear about rust, like iron, rusting, and stuff like that. Combining with oxygen, but oxygen is not the only thing that causes oxidation. We'll see how. Okay. Then obviously the other is the reducing. We'll talk about it. We'll write this down. We'll see why. Magnesium is the reducing agent. Since, according to the definition, the reducing agent is actually oxidized, but it's called the reducing agent because it makes the oxygen reduce, right? It causes O2 to reduce. Magnesium itself is actually oxidized, but it's the reducing agent. And I'm just going over this so you can attach your vocabulary. Now, then, half of it. See what done. Well, really, truly, we got them already identified, but we're going to write them out explicitly. You'll see what I mean by this. Half reaction. I will use IXN as an abbreviation for reaction quite often. But right now I will get up. Well, let's take a look at this. I have what I've identified in blue. I have magnesium changing into its magnesium ion. I'm going to write that as a half reaction. Mg. I'm going to leave space here in case I have to balance. We've already identified that this is oxidation. I'm going to put an OS for oxidation redox on the left side. There's more to it than this. And I'm going to put up here, all half reactions show the electrons involved. Okay? That's the important thing about this. I haven't shown any electrons yet. So we're going to figure it out. When I look at this, well, wait. When I look at this, Mg equals to Mg2. I'm going to look at the charge. I'm going to erase this. This is my thinking. I'm going to put a 0 here. I think when I have nothing up there, that's 0 charge, and then that's 2 plus charge on the right. Like I said, I'm going to erase it. Oh, erase too much. So, we've already talked about this. We wrote down, what did we write down? We thought about this. It loses 2 electrons. So the magnesium on the left has 2 more electrons than the magnesium ion on the left. So to show that, in a half reaction only, you lose 2 electrons. And it lost 2, right? And to make some space, 2 E negative. Okay. See how we figured that out? Essentially, though, just think about strictly the charges have to balance, not just the atoms have to balance, but the charge. If it's a total of 0 on the left, magnesium with no charge, and 2 plus on the right, always use electrons from the high side down to the low side. 0 is the low side, 2 plus is the high side. You can only add negatives, electrons. So if I look at this, I say, well, 2 groups of -1 and 2 plus, that zeroes out, that matches 0 on this side. Right? That's how we figure out the number of electrons quickly. Okay? Now the reduction, I think you need green, is the O2. So I'll put red here for the reduction. O2, switching the oxide ion. So, I have to balance this for atoms. O2, 2 oxygen atoms, so I need 2 oxide ions. Anions. I'm going to put a 2 in. When I do that, I balance for electrons. Charge. Now look at this. Now, there's 0 charge here, right? No charge. 2 negative, but I got 2 groups of 2 negatives. So I'm thinking 4 negatives on that side. I shouldn't have done that. 4 negatives on the right-hand side. I always use electrons to make the high side equal the low side. 0 is higher than 4 negative, right? I need 4 negative electrons added to the left side. So I'm going to put it from 4E minus. I'm introducing you to this. I wouldn't expect you to come up with this. Oh. There's something here, and I said you can't have reduction without oxidation. Because one thing has to lose electrons, the other thing has to gain electrons. But they have to be the same amount of electrons. You notice this one has 2 electrons coming out, this one has 4 electrons going in. That means to balance the charge, double everything on the blue reaction confirmation so that you have a balanced number of electrons. I'm going to just, I guess I'll use a different color, times 2, times 2. And when I go the blue 2 there, I'm going to just remove it. 4. So I just multiplied that. You can use an eraser or scratch it out. Okay. Now, you see how one reaction feeds the other? I think of the oxidation method, giving off the 4 electrons that are necessary for the reduction to occur. The circle. You won't have a reaction, a half reaction, occur on its own. When we add these up, it's like Hess's law took that last. I'm going to show now. Add a half reaction, a reduction reaction to an oxidation reaction. The electrons must balance. You notice that there's 4 electrons on the left. They cancel out the 4 electrons on the right. So what do you get left over? You get 2 magnesium plus an O2, making 2 groups of magnesium ion, 2 groups of oxide ion. That's not 20. 2 oxygen ion, oxide ion. And you see, basically, that's what we started. But I ripped it apart and put it back together. Actually, and I did put the 2 plus on the. I did now. You're not going to get a question. So, you'll see. Okay. Science appreciates. You know. Okay. So, next, how many seconds we got? We got 6 minutes, and we've got time to do this. This is a perfect spot. Label reduction or oxidation in balance with electrons. Okay? I'll get you started on this. First, write it down. First thing I ask you to do is label reduction or oxidation. We're just going to use read and ox. The quickest way, without even thinking about electrons, if you see charges, reduction is actually a reduction in charge. It's not the historic reason why it's called reduction. But you see the first one, cobalt, 0 to 2. That's an increase in charge. It's not reduction. So the iron, 3, reduces to a charge of 2. I'm going to put the label right here. Then I know for sure the other one's off. Done that. It helps me out. There's oil rig now. Oxidation is losing electrons. And I look at the charges on cobalt. 0 on the left, 2 plus on the right. We always bring the high side down to the low side. So 2 positives. To come down to 0, the low side, I have to add 2 negative electrons. So I'm going to put this. For the reduction is gaining electrons. So you've got to have it as a reactant on the left side of it. And it's a 3, that's the high side, down to the low side, 2. I only need 1 electron. At this moment, I have charge balance and atoms balance. Now, I'm going to try to add these equations up. Keep my arrow lined up. And I notice that my electrons aren't the same. Like fractions. I've got a 2 on the top, a 1 on the bottom. I have to multiply everything on the bottom by 2 so we have the same number. 2 times 2 times 2. Right? Here. do that, I'm ready to balance everything. The electrons cancel, so I put a light line through it. Left and the right. And then I just say, what am I left with? I'm left with cobalt plus 2 groups of iron. Cobalt, iron, 2 groups of Fe2. Now that I have this, the actual overall charge on the left side and the right side do balance. The atoms balance and the charges balance. I have cobalt 0 plus 2 times 3, 6 plus. Right, I have 2 plus 2 times 2. 0 plus. I have charge balance. We're going to leave it at this. I'm going to assign